In this video, we're going to introduce the idea of a hypothesis test. And a hypothesis test is just a statistical technique used to evaluate particular claims using data. So the idea here is you start off with a hypothesis about the situation that you're interested in, that we refer to as the null hypothesis. And you see if the data provides compelling enough evidence to move you off of your null hypothesis. That's the general idea. So of course this whole process will make a lot more sense as we go through examples. So we're going to dive right in to a particular example, and we'll run through lots of different ones throughout this chapter so that hopefully by the end of it you'll start to feel comfortable with what is a pretty complicated little process, but one that once we're finished I think you'll feel pretty comfortable with. So we'll begin with a little video to introduce this first example.
There's a domain of developmental psychology called theory of mind, which involves basically asking how do we develop an understanding of other minds? How do we come to understand other people's thoughts, their relationship between their thoughts and their behaviors?
If you both want to do different things, what could you do?
How we reason about other minds in the world. Peekaboo! We began addressing some of these questions with infants.
In this study, parents bring their 6-month-olds into the lab.
At the other side of a long table is a hill stage. A red circle guy with googly eyes tries to climb the hill. He sort of goes up the hill and then falls back down. He always fails at it. Then a blue square character, also with googly eyes, comes from the bottom of the hill and bumps him up to the top of the hill so that he's successful. On different trials, the climber tries again to get to the top of the hill, and then a yellow triangle character comes down from the top and bumps him to the bottom of the hill, so prevents him from getting his goal. Babies see this a number of times until they get nice and bored with it. So we stop and basically do a choice measure. The moms are asked to close their eyes. An experimenter who did not see which character was which brings over the two characters to the babies and just sees which character the baby touches first.
Which one do you want?
We found that, impressively actually, almost 100% of babies preferred the more positive character.
Who do you want?
Okay.
They seem to have an attraction to helpful, pro-social individuals and also a real aversion to antisocial, unhelpful individuals. Babies are fascinated by the social world.
Hey, buddy. Hey, Holland. Oh.
Young babies are all about entering the social world, making connections with different social individuals, looking at the interconnections between different social individuals and figuring out what that means. So I think these studies very nicely show how babies are evaluating individuals out in the world and how babies themselves are developing attitudes towards different individuals.
Okay, so now you've seen the video, and hopefully you found that kind of interesting and perhaps surprising that it seems that even as young as 10 months, these young children are making judgments about the type of social behavior they like and don't like. So very, very interesting. But of course, when they say that most of the infants chose the helper toy over the hinderer toy, that does beg the question, could that have just happened due to chance, right? Where the majority of the infants in the study picked the helper toy just by chance? Or is it more reasonable to assume that there is some sort of effect here that the behavior of the toy is having on the child's decision? And so as we set this up, one of the first things we'll do is set up this null hypothesis that we referred to. And some kind of things for you to key on as you learn this process is that the null hypothesis often takes on the role of saying, maybe there's no difference or no effect. In this case, no effect would mean the behavior of the toy has no effect on the likelihood that the child will choose it. And one other thing just to kind of hold on to as we're learning this process is that the null hypothesis is going to always contain an equal sign, okay? And so as we move through this particular example, you'll see what I mean by it contains an equal sign. All right, so before we do set up a null hypothesis, I do want to ask a couple preliminary questions based on stuff you've already learned. And so this would be a good time to maybe pause the video and try to answer parts A and B before watching what I write for those. All right, so if you pause and are back now, let's talk about this. So first of all, will we be collecting categorical or numerical data? Well, you can see that it says in the study, 14 out of the 16 babies picked the helper toy. So remember when we're deciding what type of data we're working with, we want to think about if I am the one recording the data, what am I writing down, right? Am I writing down numerical values or am I writing down some sort of a description of what category the person's in? And so in this case, what am I writing down? Well, the child either chose the helper or chose the hinderer. So I'm writing down helper or hinderer on my, on my data sheet. So that tells me that this is definitely categorical data. Now, if it's categorical data, remember what we learned in chapter 1 is that it's just automatic for me to say that the parameter that we would be interested in would have to be a proportion, right? If you're going to summarize categorical data, you're going to be talking about a proportion. So I'm going to write that down right off the bat. The proportion, okay? But, the proportion of what? Well, it would be the proportion of, and we want to be really specific here, we're interested in not just any infant, but the study was very careful to specify the age of these infants. So the proportion of 10-month-old infants that will choose the helper toy. So remember, a parameter is our summarizing number for the population. Okay, so we're not just talking about the 16 infants in the study here. We're talking about, of all 10-month-old infants, what proportion will choose the helper toy. And then when we talk about assigning a symbol to it, all I mean is that I want you to say, for a proportion, P is equal to this. So that way later on, as we're developing this process, we can refer to, this phrase in shorthand with just this letter P. Okay, so in part C, it says, if we are skeptical that 10-month-old children have a preference for the helper toy, what is our assumption? What is our assumption? I guess that's not a very good sentence there. That we are, there we go, that we are making about our parameter. So the null hypothesis, we talked about how it takes on the kind of no effect idea. Another way of putting it is it takes on the skeptical position. So I'm skeptical perhaps that this data, that 14 out of 16 of these babies picked the helper toy, I'm skeptical that that means really anything for the general population of 10-month-old infants. So we're going to write this out in two ways. We're going to write just out a sentence of what we mean if we're skeptical of this, and then we're going to write it out in symbols as well. What does it mean numerically? So first of all, just a sentence. Well, if I'm skeptical, then I would say something like the proportion of 10-month-old infants who will choose the helper toy is no more than half, right? Or no more than 50%. So because the child has a binary choice, either they're picking the helper or the hinderer, if we are skeptical of this idea that they actually have a preference for the helper toy, then we would say generally we don't expect them to pick, in the general population, to pick the helper toy any more than 50% of the time. And I'm going to put a little, again, we're going to use this little symbol here, H. It's called H naught, or H is just a little zero there, and that stands for the null hypothesis. Okay. Now, the other thing we want to do is be able to write our null hypothesis in symbols. And so this is where this symbol that I assign to this description up here comes into play. So basically, how do I take this sentence and put it into an equation? Well, I would be saying that I think that the proportion of the time the helper toy gets chosen in the general population is just equal to 0.5, or 50%. So that's what I mean if I say I want you to write the null hypothesis in symbols. So every time I set up a null hypothesis, I'm also going to set up its alternative, okay? And so the alternative might be the thing that we're trying to see if our data provides strong enough evidence to prove. So in this case, it says if a 10-month-old children do have a preference for the helper toy, so that'd be the alternative for them to saying that they don't, what would we say about our parameter? Okay, this is called the alternative hypothesis. So the alternative hypothesis should just contradict the null hypothesis. So I would say something like the proportion of 10-month-old infants who will choose the helper toy is more than half. Okay, so if in general 10-month-old infants tend to have a preference for the helper toy, then they should end up picking it more than 50% of the time. So in symbols, that just simply means, well, we think P is actually greater than 0.5, is actually greater than 50%. Okay, so the way we have this set up is this is kind of what the data is. We're evaluating the data to see if it kind of, we don't want to use the word prove, but provides evidence for this. And then in order for it to do that, we're starting off with the assumption that, nothing's going on here, that it's just equal to 50%. So this is our starting assumption right here, and we have to have compelling evidence for us to switch from the null hypothesis to the alternative hypothesis. So a good analogy for this is, if someone's being put on trial for something, for some sort of crime, in our system of justice, we presume them innocent at the beginning, right? And so there's a presumption of innocence, and only if the evidence that the prosecution presents is really compelling, right? The term is beyond a reasonable doubt. Only then do we change our mind from saying innocent to guilty. So it's the same thing here. The null hypothesis here is kind of like, okay, I'm assuming that the defendant is innocent. And the alternative hypothesis, we can only switch to that if the data is really, really compelling for us to do so. All right, so next part E here, asks us to calculate the sample statistic in this study. So remember from chapter 1, when we say statistic, we're talking about the same measurement as our parameter, but for the actual data from our data set. So for us, we're interested in the proportion of the time that the helper gets chosen. Okay, so we're going to say P, and then to designate that it's for a sample, we're going to use this little hat on here. So P with a hat tells you, okay, this information is coming from the sample. And I can see that 14 out of the 16 chose the helper toy, which comes out to 0.875. Okay? So this is telling me that in our small little study here, the helper toy was chosen 87.5% of the time. Now that's clearly more than 50%, right? But we also know that random variability happens, right? So the question we now have to answer is, when you get something like 87.5%, when you were starting with the idea that you thought that the percentage should be 50, does that provide enough evidence for you to now conclude, okay, I think actually it is greater, that there is a preference for the helper toy? That's what we have to figure out. So that's what we're going to do in part F. It says, if we assume the null hypothesis is true, how could we simulate this study? Okay, so what do I mean by that? What I mean is, how could we just use everyday objects to simulate what it's like to present each 10-month-old infant with the choice of a helper or hinderer? Well, if the null hypothesis is true, right? If that's what we're working off of, then that means we're assuming that the percentage is 50%. And if this percentage is 50%, then what we're essentially saying is that the infant's choice is essentially like a coin flip, right? They're just doing it randomly. And so we might as well be flipping a coin heads or tails and deciding helper or hinderer based on that. And so that analogy is exactly how we're going to actually simulate this study. So what we're going to do is we're going to flip a coin the same number of times as there were subjects in the study, 16 times. Okay. I flip the coin 16 times, and for each flip, we're going to say heads is going to be the same as picking the helper. And tails is going to equal picking the hinderer. All right? And so what we're going to try to do here is try to get a sense of, if choosing helper or hinderer toy is just like a coin flip, then if I flip a coin 16 times, how often does something like 14 out of 16 actually come up? Right? That's the question that I want to answer. All right. And what we'll do, of course, is we'll then record after we do this. We'll record the number of heads divided by 16, right? And then that gives me the same exact measurement as my actual sample. And so how often do we see results like our sample? That's really what we're trying to answer. All right, so part G wants us to execute this plan, okay? And it wants us to execute it multiple times. So what I'm going to do here is open up our course site here, and I want to show you how to get to the tool that I'm going to use before I use it, because it'll be something that you may use for some assignments and projects. So in important class links and documents, at the very bottom, there's this block here called the Rossmann-Chance Applet Collection. So I'm going to open that up. If you click on this first one, it just takes you to a general menu of lots and lots of different tools they have. But what I'm going to do, and so you might, use this menu at some point. But I've also directly linked to the things that you're going to use right away. And so one thing you're going to use right away is one proportion inference. Okay. So in our problem here, we are dealing with one single proportion, right? So I'm going to click on this, okay? And there's a whole bunch of stuff here, so I'll try to kind of walk us through this. In this first slot is where I'm going to put the probability of heads. So what is that really in regards to our hypothesis test? It's our null hypothesis. So really quickly going back here, a couple of slides. So here's my null hypothesis, p equals 0.5. So if it was equal to something else, if I said p equals 0.3, then in that spot, I would put 0.3, right? So whatever your null value is, that's what you're putting there. And then we already said that we're going to toss the coin 16 times. Okay, so I'll put that in there. And right now I'm just going to do this once to start with. So I'm going to hit draw sample. And you can see it's going to flip a penny 16 times. And it's recording for us the number of heads and the number of tails. And so in this case, 6 heads out of 16 tosses is what we got, right? So put a little dot right there. I'm going to hit it again. I got the same result again here actually. 6 heads out of 16 tosses. So I put another little dot right there. Do one more. Okay, now we got a different result. This time 9 heads out of 16 tosses. Okay, so just in the flipping of a coin we see variability, right? One more here. Now we're back to 6 out of 16 again, right? So we don't expect, when we look at data, we don't expect it to always be the same, right? Data's messy, and we're seeing this in the coin flipping. So what I want to do, though, is I want to collect 100 of these, right? So essentially, flipping the coin 16 times, recording how many heads we get, and then repeating that 99 more times, so that we have a total of 100. So there'll be a total of 100 dots down here in this chart. So we've already done 4 of them, so let's do 96 more. And don't worry, it's not going to go through this whole thing. I'm going to unclick the show animation. All right, so after 96 more tries, this is what my chart looks like, okay? So down here, it's keeping track of the number of heads that we flipped. And what I'm going to do now is in part part E of what we're completing right now, or excuse me, not part E, part G, we're going to go ahead and sketch this chart. Okay, so it'll take us a minute here, but it'll be worth doing so that as you look back on this, it'll make a lot of sense to you. So we executed our plan multiple times. So we're going to create a dot plot now. All right, so we just want to make to start here, a horizontal line. All right, and we understand that, of course, this would represent 0 heads, 1, 2, 3, 4. So we'll just do this, 5, 6, 7. And on the one hand, what I'd like to do is label this according to what our simulation was. So on the one hand, this is the number of heads. That's what these numbers mean. But on the other hand, what is it representing, right? The number of heads is representing the number of times out of 16 that the helper is chosen, right? That's what each head represented for us. All right, so I can go ahead and plot this, and I'm going to switch colors here, I think. So do this in orange. So on 0, 1, and 2, I don't have anything. On number 3, I've got 1 dot. On 4, I have 1, 2, 3 dots. On, let's see, on 5, I have 5 dots. And then on 6, I have quite a few. I have 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And I think it'd be helpful if we kind of write these up at the top. All right, just to give the total as we go. On 7, I have 18. On 8, I have 17. On 9, I have 22. And by the way, as we're doing this, I know this is tedious, and this is not something that I'm normally going to ask you to do. But I want a really clear record in your notes because, as I said, this can be a challenging section. And so I want you to be able to come back to this and understand why it is that we're going to be drawing the conclusions we're drawing. All right, so then in 10, I have 12 of them. And then in 11, I have 8. And that's it, okay? So what we've just done here, we refer to this thing as a sampling distribution. I'm going to label it with that because you hear that word a lot. This is a sampling distribution. And it's just telling me what the kind of how things shake out if we're assuming that the null hypothesis is true. How would studies of this nature look? And you can see there's lots of variety in how the study might turn out if the null hypothesis were true. But here's where this helps us come to our conclusions. In part H it says, what percent of your simulations generated a statistic? Each one of these dots is a statistic, 3 out of 16, right? These are 4 out of 16, and so on. Generated a statistic as extreme or more extreme than what you observed. So let's remember that 14 is what we actually observed, right? This was the observed value in the actual study. So when they say what percent of your simulations generated a statistic as extreme, so out here or even further away from the assumption, which is that, 8 out of 16 is what you would expect, well, the answer to that is it didn't happen. So in all of our tries, in all of our simulations of flipping coins, we never, right? We never observed a simulation that generated a statistic of 14 out of 16 or greater. Never happened. Okay? Never happened. So let's now bring this back to our null hypothesis and our alternative hypothesis. So remember we started off with the idea that the true proportion is 50%, right? Is 0.5. So the null hypothesis is that p is equal to 0.5. We conducted these simulations assuming that p equals 0.5 is the true proportion. All right? So the fact that we never observed a simulation that generated a statistic of 14 out of 16 or greater meant, another way of saying it is that we observed it 0% of the time. When it asks what percent, we would say 0%. This is what's called our p-value. So our p-value here was 0. And that just means if the null were true, we wouldn't expect to see samples like ours at all. So either something happened that we really don't expect to happen much at all, and in fact it never happened when we tried to simulate it, or the null hypothesis was false. Okay? And so what we do is we look at this p-value, and anytime it's less than 5% or 0.05, that's when we say the most reasonable thing to do is to reject our null hypothesis. So we reject the null hypothesis, and we'll just say because we don't expect to see samples like the one from the study, if the null were true. That's why we reject. Now, if our sample from the study, let's say 11 out of the 16 infants chose the helper, well, you can see that that happened pretty often, even when the null was true, right? So this idea that we're checking to see how often our sample shows up in these simulations, and when it doesn't show up or it shows up very little, that's when we say the null hypothesis was probably false to begin with. All right. So in part J, it says write out a clear conclusion about your alternative hypothesis. And on the next slide, I'll show you kind of a good template to start with when you're writing out conclusions. Generally, what we want to say is either there is or is not enough evidence to say that the alternative is true. So if we reject the null hypothesis, then we are saying that the alternative hypothesis is true. So I would say there is enough evidence at the, and it's always good to declare this, what we call the level of significance, which is that threshold we set to say if our p-value is smaller than this, we reject. At the 5% level of significance, to suggest that the alternative is true, right? And remember, the alternative was that the proportion of 10-month-old infants who will pick the helper is more than half. All right, so that's how we write out a conclusion about our alternative hypothesis. Okay, so just to kind of wrap this up, and I know these examples, there's a lot of moving parts to them. We're going to do lots of examples, so don't worry about that. And I just want to kind of finish this video by just talking about the steps we just went through. So number one, we determined our parameter of interest. We said we're interested in the proportion of 10-month-olds who will choose the helper toy. We wrote out a null and alternative hypothesis, right? And the null hypothesis, we came at from the idea that we were being skeptical, or we thought that there was no effect, right? The toy's behavior had no effect on the likelihood of being chosen. So we wrote out the null and then the alternative hypothesis, okay? And I just want to, over on the side here, this would be a good thing to, when you're trying to determine a null hypothesis, here's some phrases that help. We used this one, skeptical. Okay. No effect. No difference. We also talked about how it's always going to contain the equal sign. Okay, so these are all just kind of key phrases, and if you can apply one of these phrases to the situation that you're studying, then it's a good bet that that is your null hypothesis that you want to go with. Okay, and we'll talk about this more as we go into future examples. We determined the sample statistic, right? So this was, when we said, all right, 14 out of the 16 infants picked the helper toy. We found the p-value, right? The p-value, remember, for us was 0. So the p-value is the proportion of the time that you would expect to see samples as extreme as yours or more extreme. Okay, and again, what do I mean by as extreme or more extreme? More as or more extreme than our sample based on the null hypothesis. So the null hypothesis was, is the null values right here in the center, right? 50% is what we were assuming. So to say a sample like ours or more extreme would be to say, how often, what proportion of the time do you get results like this? 14, 15, or 16. That's the p-value. For us, the answer was 0. Okay, and we'll look at lots of examples where it's not 0. All right, and then we have to make our decision, okay? And our decision is based on something we call that level of significance, and we talked about that briefly in the example. Often, and so I use this symbol alpha for the level of significance. Often we use 0.05. Not all the time, but the reason 0.05 is a kind of a good marker is 0.05 or 5% is 1 out of 20. And so if you think of something happening 1 out of every 20 times, that's pretty rare, right? So what we're saying there is that if our p-value, right, how often I expect to see samples like mine, is 1 out of 20 or less, or 5% of the time or less, then the fact that my sample did turn out that way makes me fairly comfortable saying, well, you know what, I'm kind of thinking maybe the null hypothesis is incorrect. So if the p-value is less than or equal to the level of significance, then we reject the null hypothesis, right? In our example we just did, our p-value was 0, right? And the level of significance was 0.05 or 5%, and so clearly 0 is less than that. That's why we reject it. But if it's greater than the level of significance, then that's when we fail to reject the null. There's not enough evidence to do so. And just a little terminology here. If we reject the null hypothesis, then we say that the data provide statistically significant evidence against the null hypothesis. So going back to the beginning here, the fact that 14 out of 16 infants chose the helper toy is statistically significant evidence against the idea that the infants are just randomly guessing, right? And it's statistically significant evidence in favor of the idea that actually they have a preference for the helper toy. All right, and then finally we wrote a conclusion, right? And here's that template that I promised you. And if you look back at the previous page, you'll notice I really followed this. So you're going to say either there is or isn't enough evidence at the 5% level or whatever percent level of significance to suggest the alternative is true. And you'd say that, of course, there is enough evidence when you reject the null hypothesis, and you say there isn't enough evidence when you fail to reject the null hypothesis. All right, so we'll come back to these steps as we do future examples. I know this was a big example. If you feel overwhelmed, just know that we're going to spend a lot of time on this, and we're really going to take our time working through this. I'm not going to rush you through it because you know, this is some challenging stuff, but you're going to get it.